Alors, bonsoir à tous et bienvenue à cette grande conférence du Centre de recherche mathématiques. Elle a lieu en 2022. Alors, tous les 4 ans, il y a le Congrès international des mathématiciens, lors duquel une cérémonie à l'ouverture et les médailles Fields, c'est l'équivalent du prix Nobel en mathématiques, sont dévoilées. Donc, la cérémonie a lieu tous les 4 ans. Elle a eu lieu le 5 juillet et nous avons la chance ce soir d'accueillir un des 4 récipiendaires de la médaille Fields, James Maynard. James Maynard a fait son doctorat à Oxford en 2013 et son premier postdoc, ça a été au Centre de recherche mathématiques ici à Montréal. Donc, il a des amis et des collaborateurs à Montréal. Il a fait d'autres postdocs à Berkeley, à Princeton, à Oxford, et il a maintenant un poste au Mathematical Institute d'Oxford depuis 2017. Sa recherche porte sur les écarts entre les nombres premiers. Dès son doctorat, il a obtenu des résultats spectaculaires. Je dirais que sa recherche est caractérisée par l'audace et la créativité. L'audace, il y a des décennies, il y a des méthodes qui sont là, qui n'ont pas fait leur preuve, et pourtant, il faut se dire, on peut pousser les méthodes plus loin et on peut obtenir des choses là où personne ne les attend. Donc, c'est vraiment comme ça qu'il a fait sa recherche et que ses résultats ont été reconnus. D'ailleurs, il était déjà conférencier invité au Congrès international des mathématiciens de 2018. Alors, sa recherche lui a mérité de nombreux prix. Pour ça, j'ai besoin de mon papier. Donc, un prix Erdos, un prix Sastra Ramanujan en 2014, un prix Whitehead en 2015, un prix de l'European Mathematical Society en 2007. Alors, ce soir, nous sommes vraiment heureux qu'il soit parmi nous, qu'il ait accepté de nous parler. Le titre de sa conférence, The Magic of the Primes.
Thank you very much, Christiane, for inviting me for the very nice introduction, and thanks for the invitation to give this public lecture here at Montreal. It's always a pleasure to be back in Montreal. I had a great time when I was a postdoc here. So the main thing I'd like to talk about today is to give a feeling for why I think the study of prime numbers is an absolutely beautiful, fascinating subject in mathematics, but as well as being beautiful and fascinating for mathematicians, is also a sort of fundamental and really important subject for the whole of science. So maybe the most basic question that I want to talk to you about is my answer to why should we care about prime numbers? Why are prime numbers interesting? Why should you be interested in prime numbers, as well as why am I interested in prime numbers? And maybe the tagline for the whole talk, if you're feeling a little bit sleepy and you're not sure you're going to listen to anything after the first minute, the key point I want to make is that primes are somehow really fundamental objects to the whole universe. They underlie mathematics and they underlie all kinds of other objects. But despite them being some of the most basic and fundamental objects in mathematics, they remain completely mysterious, and problems that are exceptionally simple to state and have been studied for thousands of years remain completely beyond the best mathematicians today. And it's this combination of being both, on one level, the most fundamental basic objects in mathematics, and on the other hand, being mysterious and poorly understood, which is why I find prime numbers so compelling. I want to sort of make this case for prime numbers in 4 key steps. I want to explain why prime numbers are these building blocks in mathematics that is the reason why they're not just some strange curiosity, but actually really important objects within mathematics. And I want to then demonstrate this, giving you 2 examples. One example in the real world, and how prime numbers can be useful even if you couldn't care anything about mathematics. And another example, right in the opposite end of the spectrum in pure mathematics, how prime numbers play vital roles in basic questions, even if at first sight they don't seem to have anything to do with prime numbers. And then finally, I'd like to finish up by mentioning a little bit of new progress on these old problems, that despite the fact that there's all these big questions about prime numbers that are very famous and have sometimes go back to the ancient Greeks, even these problems that are hundreds and hundreds of years old, the subject doesn't just stop there. We don't give up, and we are able to make progress on some of these old famous problems. And so mathematics is very alive, and it's an exciting time to be studying prime numbers. My first step is primes as building blocks, with a slightly blurred picture of building blocks. Just so we're all on the same page, let's remind ourselves, what are prime numbers? If you ask a mathematician to define what a prime number is, then they might give you a slightly dry definition like this, that a prime number is a whole number which is bigger than 1 and can't be written as a times b for two smaller whole numbers, a times b. So, for example, 15 is not a prime number because it can be written as two smaller whole numbers multiplied together, because it can be written as 3 times 5. But 7 is a prime number because we can only write 7 as 7 times 1. There's no way of writing it as two numbers multiplied together where they're both smaller than 7. You always have to have 7 times 1 or 1 times 7 or something like that. So if you see this definition and you work out a few examples, I claim that the obvious question is, why on earth should you care about this? This looks like a completely arbitrary thing that you're looking at, and maybe this is some idle mathematical curiosity, but certainly not some important objects. And the real point of this definition is that primes, this definition doesn't make it clear, but it turns out that with this definition, primes are really the building blocks of whole numbers, and every number can be made up of prime numbers. And this means there's always this dream that if you have some complicated question about whole numbers, you might reduce it down to some simpler question about prime numbers. And scientists in general are lazy. You know, we don't want to have to work really, really hard for things. What we would really like is to be able to understand some big complicated objects by just understanding simpler objects. That makes our life a lot easier. It makes there much less work to be done. And there's this fundamental principle that is ubiquitous across the whole of science, where you shouldn't try and understand some very complex, complicated system all in one go straight away. A very, very fruitful way for science to try and understand some system is to try and break it down into much simpler building blocks. And if you can hope that if you can understand the fundamentals of small aspects of how pieces interact, then you can understand this big complicated system. A few examples of this: if you're a chemist, then you're interested in studying, amongst other things, chemical compounds. And we know that you can understand not all properties, but lots of important properties about chemical compounds by understanding the atomic elements that make up that chemical compound. So this is an example of a big complicated object like a string of proteins. You can get some partial understanding by understanding the constituent atoms that make up these proteins and how they're joined together. Similarly, if you're a geneticist, then you're maybe interested in genetic phenotypes and properties of consequences of the genome, and therefore it's, rather than trying to understand this, all the complexities of human genomics, it turns out it's very fruitful to focus on individual genes and the base pairs that make up those genes. That way you can study individual mutations and things like that. And so looking at individual base pairs and breaking this down into the genetic code turns out to be an exceptionally useful way of taking this big complicated problem of the whole genetics of a human and reducing it down to a simpler problem about understanding the different constituent parts of genes and alleles. So that's that principle again. And how would that principle then work for people like me, who are number theorists, who are mathematicians, whose main object of study is not chemicals or genes, but instead the whole numbers? That's sort of what a number theorist is. Fundamentally, we're trying to understand the whole numbers. Well, there's maybe two key properties of two key operations that you can do with whole numbers that you learn in high school or before high school: addition and multiplication. These are the two sort of fundamental properties. And from the point of view of addition, all whole numbers are generated just by the number 1. You can get to any whole number by just keep on adding 1. So you start off with just 1, and then 2 is 1 plus 1, and 3 is 1 plus 1 plus 1. And because whole numbers are generated just by adding 1 each time. Many questions about whole numbers, you can sort of simplify them to just the constituent parts, which is just understand this operation of adding 1. And this means that many purely additive questions turn out to actually be quite easy, because there's this one nice fundamental generating way of getting to every whole number by just adding 1 each time. If instead of looking at addition, you look at multiplication, then suddenly the whole picture becomes much more complicated. So rather than whole numbers now being generated by 1, whole numbers are generated by prime numbers. That every number, it turns out, can be broken down into prime numbers, because you can always, if you're not a prime number, you can always write it as a times b for smaller numbers a and b, and you can keep on doing this until you write a number as prime numbers multiplied together. But once you've written a whole numbers, prime numbers multiplied together, you can't break it down any further. And so this means that the atoms of multiplication, if you like, are the prime numbers. And so if you have some question about whole numbers which involves multiplication, then you might hope to answer this question about whole numbers and multiplication by turning it into a question about prime numbers. And if you can understand the prime numbers, then you can understand whole numbers and how they work with multiplication. But unfortunately, this is quite a bit more difficult than in the case of addition, because rather than there just being one number that generates everything, suddenly there's this whole sequence of prime numbers, and you have to understand all the prime numbers if you want to understand the original problem. The fundamental theorem of arithmetic is the fancy name that mathematicians call the key property. So we call this a theorem. It goes all the way back to the ancient Greeks, and this is really why mathematicians care about prime numbers. And it's what I already said when we were at the previous slide, that every whole number can be written as prime numbers multiplied together, and there's only one way to possibly do this. So if you think of a whole number as some sort of chemical compound, then the atoms of that chemical compound can be thought of as the prime numbers which multiply together to give the overall number. This graphic is supposed to be showing 135 as a complex chemical, and the atoms that make up that complex chemical are the prime numbers. And if you repeatedly try and break 135 down, you find that you can write it as 5 times 3 times 3 times 3. And this is the only way of writing those whole numbers multiplied together, apart from possibly sort of multiplying by 1 and things. And therefore, because the prime numbers are these building blocks, these atoms of multiplication, that they seem to be really fundamental objects to mathematicians. That multiplication is one of the most basic things that people learn in elementary school, and the atoms of this most basic operation are therefore the prime numbers. And so they seem like the most basic constituent objects of mathematics, to me at least, in the same way I imagine a chemist views the different chemical atoms, the elements, as the most fundamental building blocks of chemistry. So there's lots of fancy quotes of different people. One famous mathematician is called Kronecker, and in translation, his quote is that God made the whole numbers, and everything else is the work of man. And so this is somehow saying that, there's only one really fundamentally natural object to mathematicians, which is the whole numbers, and these are really underlined by the prime numbers. Prime numbers are these really important fundamental building blocks, but the crazy thing about prime numbers is that even though they seem to be these natural and basic objects, even fairly basic questions about the prime numbers remain very poorly understood by mathematicians. And so it's this contrast between being important but poorly understood despite our best efforts, which really makes primes this sort of fascinating subject. So there's a quote I really like of another famous mathematician, Don Zagier, who says, despite their simple definition and role as the building blocks of the natural numbers, the prime numbers grow like weeds amongst the natural numbers, seeming to obey no other law than that of chance, and nobody can predict where the next one will sprout. And this really sort of summarizes the situation, that they're both fundamental, but at the same time mysterious, and we don't really understand them very well at all. So just to give an example of this, you could consider how many prime numbers there are. So if you give me some large number, maybe 1 million, maybe 1 billion, the challenge would be roughly how many prime numbers are there which are less than 1 million or less than 1 billion or less than whatever number you chose. And if you make this question a little bit more precise, this is a form of the Riemann hypothesis, which is often dubbed the most important and famous problem in mathematics. It's based on the distribution of prime numbers, and if you solve the Riemann hypothesis, which would mean given a good answer to this question, then even if you don't care about prime numbers, you get $1 million for solving it. So that's another reason to care about prime numbers. Okay, so I'd now like to try and give my first example of this contrast between primes being fundamental and mysterious by a relatively real-world example. And my example is going to be buying something on Amazon. So I'm a mathematician, so if I go and buy something on Amazon, I'm probably doing something dull and buying a number 3 math book or something like that. So yeah, imagine you want to buy something on Amazon and maybe you have slightly more interesting tastes than me in what you might buy. Well, if you want to buy something on Amazon, you probably also don't want some other nefarious person to be able to hack your credit card details and to steal all the money out of your bank account. So it's very important that when you're sitting at your computer looking at number theory textbooks that you might want to buy, and you're communicating with the Amazon servers, there's not some evil person who's going to take all your details. And the way that your transactions on Amazon are kept secure is by turning your secret information, or the information that you want to keep secret at least, such as your credit card details, into a number, and then encrypting it using some algorithm to make it very difficult for any potential hacker to decrypt and work out what your credit card details are. And this way you can communicate securely with Amazon without anyone being able to interfere. But then a natural question is, well, how on earth can you go about making this system where you can securely encrypt your credit card details in such a way that Amazon can still understand what's going on, but any potential hacker can't understand what's going on? And it turns out that when you start looking at lots of the crypto systems that different computer scientists have come up with, often they involve turning your credit card details into numbers and multiplying these numbers together. This is somehow some of the most basic operations. And because it's involving whole numbers and multiplication, if you were a hacker who was trying to hack someone's credit card details, you might think this is a problem involving whole numbers and multiplication. And so I could try and use prime numbers to understand what's going on, because prime numbers are the building blocks of multiplication. And it turns out that actually for many of the most common cryptographic systems, in principle, you could try and use prime numbers to hack people's credit card details. So the point of this lecture is not to give you hints on how you can steal credit card details of other people, but fundamentally, if you really want to hack someone's Amazon credit card details, often the key question is just, if I give you a big number, can you turn it into the prime number? Can you write it as prime numbers multiplied together? So we saw before that every number can be broken down into prime numbers. And if you can do that for a really big number, it turns out that actually you can hack other people's credit card details and you can steal all their bank accounts and things like that. So fortunately, you shouldn't stop buying everything from Amazon. You can still buy things online, because we believe it's very difficult to turn a number into its prime factors when those numbers are very large. So one simple example is you could take, for example, the number 449,623. And the question is, what are its prime factors? So I guess everyone in the audience has probably worked it out that this is obviously 521 times 863, which are the two prime factors of 449,623. But maybe it wasn't totally immediate for you what those numbers were. And that's because actually this does become a very, very difficult problem, we think, when the numbers involved get very, very large. So to have one concrete example, here's another number that we could write down. And if you're able to write this number down as a product of prime numbers, you get a reward of $75,000. So those of you who found this first example a little bit too easy, why don't you try this one and see if you can do that? And if you can, $75,000. Not quite as much as the Riemann hypothesis, but it's still not too bad. And there's lots more of these bounty problems of very large numbers. And can you factor these? And if there was some efficient procedure for turning these very big numbers into prime numbers multiplied together, then there would be a very efficient procedure for hacking and breaking lots of these cryptographic systems that are really fundamental to the internet and to e-commerce in general. But the interesting thing is that you could try and think about this problem by studying prime numbers a little bit more. And it turns out that this problem of turning a very big number into prime numbers multiplied together, we think it's a difficult problem in general, but if basically your big number has prime factors, let's say p, where when you take away one, that itself only has small prime factors, then you can use techniques from number theory to actually turn this number into lots of small prime factors. So we expect that this should be quite rare, but if you have this strange situation where you have unusual prime factors, then you can use the power of prime numbers to factor numbers. So for example, you could take the number which is 2 times 3 times 4 times 5 up to times 320 and then add 1. And this way, when I take away 1, this number only has prime factors which are smaller than 320. And then you can take some other very large prime number q and look at this number turns out to be a prime number. You could look at q type that number times p. And even if you didn't tell me that p was a factor, because this very large number has this special prime number as a factor, it turns out that you can use this clever algorithm based on prime numbers, and you could factor it almost instantly. And this number here is much, much bigger than the number I put on the previous slide, where you get $75,000. So the point is that even if the numbers get really, really big, there are some numbers where you can still use prime numbers to understand what's going on, and you could still hack someone's details. And therefore, this might be a little bit concerning for you. You know, you want to buy something on Amazon, you don't want someone to steal your credit card details. Your computer's going to pick some number, but you know that this number is really not secure at all if your computer picks some number where you had these prime factors where p-1 had lots of small prime factors. So if you want to be able to buy things securely, you want your computer to pick a good number. And so you should be a little bit concerned about how often would it be the case that my computer could pick a bad number. And so another way of saying that is, if I take some prime number and I take away 1, how often would that resulting number just have lots of small prime factors? This is sort of how likely is it that my computer would choose an insecure number. And this is now a problem that you can give to a mathematician who studies prime numbers. And we do know a bit about this sort of question. And so we have various results that sort of say that it's very rare for p-1 to only have lots of small prime factors. So it would be very, very unlikely that your computer would choose some insecure number and someone would be able to easily hack your credit card details. But, you know, you might say, okay, James, it's not very likely, but I don't want to be the guy who has all my bank account details stolen. You know, if you're willing to put your money up for that, then fine. And so, because even though we think it should in general be fairly safe, some people have suggested avoiding this situation by getting your computer to check you're very far away from ever having this property of p-1 having lots of small prime factors. Now, if p is a very big prime number, then p is going to be not going to be an even number, it's going to be an odd number, because if it was even, it would be a multiple of 2, and so it couldn't be a prime number. So whenever you have a big prime number and you take away 1, that has to be a multiple of 2. So you always have to have one small factor in there. But maybe the furthest you could be away from this p-1 only having small prime factors would be if p-1 divided by 2 is also a prime number. So there's no other factors at all, and it has this really big number. And that's about as far away as you could possibly be from p-1 having only small prime factors. And so these prime numbers p, where p-1 divided by 2 is itself a prime number, so-called safe primes, and even in some modern cryptographic systems, this is some of the pages for explaining how to use OpenSSL, which is one of the commonly used cryptographic systems. You have the opportunity to make sure that the number your computer chooses is only involving safe primes, these prime numbers p, where p-1 divided by 2 is also a prime number. Then again, you have a bit of a potential problem, because although you've got around all the issues of p-1 only having lots of small prime factors, this would be a really bad idea if there were only 5 prime numbers where p-1 divided by 2 was a prime number, because if I was a hacker, all I would need to do is to try that list of 5 prime numbers. And so then if you're a little bit paranoid, you might say, well, hang on, how many prime numbers are there with p-1 divided by 2 also a prime number? You know, this comes up in cryptographic themes. I want my Amazon purchase to be really secure. I really want to buy that book. And this is actually a famous open problem in the study of prime numbers. So this is a problem which has been open for well over 100 years. It was started way before computers existed in any shape or form, and we don't know how to solve this problem. We don't know how many primes there are where p-1 divided by 2 is a prime number, but we believe at least that there should be lots of them, and so we believe that this should be a perfectly safe way of making your purchase on Amazon. So yeah, this is, you could rewrite this example as, can we solve one equation, p, where you have 1 prime, you take away 1, and that's equal to 2 times another prime. And so this is some equation where the variables are now prime numbers, and this is just one example of a whole zoo of different possible equations that people like me and number theorists study to see when there are solutions in prime numbers and when there aren't solutions in prime numbers to these equations, and they underlie lots of different problems. Whenever you have whole numbers involving multiplication, you can imagine it boiling down to questions about prime numbers, and when do prime numbers solve certain equations like this. And this is the particular one that came up from this example about cryptographic systems. And yeah, the fascinating thing is these very natural questions that at first sight have got nothing to do with prime numbers. It's just, you know, some computers multiplying some numbers together. Quite quickly, you get into these very difficult questions about prime numbers, and when do prime numbers start solving certain equations and when do they not. Okay, so that was one real world example about you going on your computer and buying something on Amazon. My second example, I want to shift gears slightly and take the point of view of a pure mathematician who wants to solve equations. And I'm going to look at the most famous equation in the whole of pure mathematics, basically, which is Fermat's last theorem. So Fermat was a French mathematician, and he famously claimed that there should be no solutions to the equation a to the power n plus b to the power n equals c to the power n, where a, b, and c and n are or all whole numbers with n being bigger than 2. I guess you're not allowed to have 0 as one of your numbers either. So this was this very famous problem, which had been open in mathematics for a huge amount of time. A huge amount of new mathematics was developed precisely to try and answer this problem. And then very famously, this was solved by one of my colleagues in Oxford now, actually, Andrew Wiles. And he showed that Fermat's last theorem is indeed true, and there are no solutions to this equation a to the power n plus b to the power n equals c to the power n, apart from the obvious ones. Okay, so why might this be? So this is some equation that's interested pure mathematicians for a huge amount of time trying to solve equations. But the thing to notice is, again, it involves whole numbers being multiplied together. And when you have whole numbers being multiplied together, you might think that you can use prime numbers to try and help you solve this sort of equation. So one way that this works is that it turns out it's enough, if you want to solve Fermat's last theorem, you don't need to consider every possible number n which is bigger than 2. It's enough to just consider prime numbers n which are bigger than 2. So rather than having to look at every possible number, you can just look at prime numbers, and then you might hope to use special properties of prime numbers, which makes your life easier at solving Fermat's last theorem. And the proof of this maybe involves a little bit of high school arithmetic, but I can sketch the idea just here. So imagine Fermat's last theorem was false, and so there were some a, b, c, and n such that a to the n plus b to the n was equal to c to the n. And for the sake of argument, let's imagine it was false when n is equal to 15. So there's some a, b, and c, which are whole numbers, with a to the power 15 plus b to the power 15 equals c to the power 15. A to the power 15 is a times a times a times a 15 times. So another way of writing that would be a times a times a 5 times, and then multiply that number by itself 3 times. So in mathematical notation, that's a to the power 15 is a to the power 5 to the power 3. And doing that for all of these things would mean that a to the power 5 to the power 3 plus b to the power 5 to the power 3 would equal c to the power 5 to the power 3, because we know that a to the 15 plus b to the 15 equals c to the 15. But this means that we've now got a counterexample to Fermat's last theorem when the exponent is not 15, but 3, because we can use a to the power 5, b to the power 5, and c to the power 5. And so this means that any counterexample when n is 15 produces a counterexample when n is 3. And if you think about this argument a little bit, this means that whenever you have a number which is not a prime number, if you write it as its prime factors, you can do exactly this same argument and get a counterexample for every prime factor of n. This way, you don't need to consider the case when n is 15. It's sufficient to just prove there's no solutions when n is 3, and that automatically implies there's no solutions for n is 15. And similarly, if you knew this was the case for every prime number n, then because every number is made up of prime numbers multiplied together, you get the whole of Fermat's last theorem. And so we've taken the whole of Fermat's last theorem and we've reduced it down to a problem just involving prime numbers in the exponent n. So it turns out that this is essentially the first step in Andrew Wiles's proof of Fermat's last theorem. Unfortunately, there's not quite enough space in the slide here for me to finish the full proof. But you kind of get the gist. Okay, so Andrew Wiles's work is an absolute pinnacle of lots of modern mathematics that's been developed. But there was certainly lots of important earlier work that made partial progress on Fermat's last theorem. And maybe that's an easy way for me to explain how prime numbers can be involved in other ways as well. And so one of the people who did very important work on Fermat's last theorem in the 19th century was Sophie Germain. So she proved a very important theorem about solutions to Fermat's last theorem. So if you remember, we only need to consider Fermat's last theorem when n is a prime number. So we're now thinking of n is, I'll call it p for prime number. And if p is a prime number such that 2p plus 1 is also a prime number, then she was able to use properties of prime numbers to show essentially that there's no solutions to a to the power p plus b to the power p is equal to c to the power p. So there's a technical thing about ABC not being a multiple of p. This is known as the first case of Fermat's last theorem. Everyone who was working on Fermat's last theorem sort of split Fermat's last theorem into the first case and then the second case, and they thought that once you solved the first case, you could kind of work a bit harder and do the second case, but this was the important case. And she was able to solve this whenever you had when n was a prime p, such that 2p plus 1 was another prime. So based on this great theorem of Sophie Germain, she was able to solve lots and lots of cases of Fermat's last theorem. She wasn't able to solve the whole problem, but she was able to rule out lots and lots of exponents, and she had done way better than anyone else had done at that time. But once you see Sophie Germain's theorem, a natural question is, well, okay, so how often does this actually work? And so the natural question is, how many primes are there such that 2p plus 1 is also a prime number? So again, we've taken a problem from whole numbers, we're studying Fermat's last theorem, and we very naturally got out a problem to do just with prime numbers. And for those of you who've been paying attention, you might recognize that this is exactly the same problem as I had before with the real world example, where I was looking at p minus 1 divided by 2 being a prime number. If p minus 1 divided by 2 is a prime number, then we have a prime p such that 2p plus 1 is a prime number. And so this is somehow showing the ubiquity of prime numbers across all these different examples, that we have one example which came way after the ancient Greeks or anything like that, coming from computer science, about whether your Amazon credit card details are secure. And then we have this other example from work of 19th century mathematicians solving totally pure math equations. And in both cases, we've seen that there's these very natural questions about prime numbers trying to solve equations that come up. And in fact, it's the same questions about prime numbers. Unfortunately, of course, this means that it's the same problem that has been open for hundreds of years and mathematicians haven't been able to solve. So we don't know how many primes there are such that 2p plus 1 is a prime number. And so therefore, we don't know quite how many cases Sophie Germain's theorem. So I'm making good time. And hopefully I've therefore convinced you with these two different examples that prime numbers crop up in all kinds of different places whenever you have whole numbers involved in multiplication. And as soon as you start to look at whole numbers involved in multiplication, you can use prime numbers to your benefit. Remember, the whole point is that we're lazy mathematicians and we don't want to have to solve complicated equations. We want to solve simpler ones. And we're thinking these questions about prime numbers are the simpler ones, even if we don't know how to solve those questions about prime numbers. But regardless of the situation, whenever you have whole numbers multiplied together, you very naturally get these questions coming up about prime numbers and the distribution of prime numbers. And so it's this distribution of prime numbers, which is a topic that has fascinated mathematicians for thousands of years and is the main thing that I work on. So I'm not really an expert on cryptographic systems. I don't work on Fermat's last theorem, but I really do work on the distribution of prime numbers and how often prime numbers solve certain equations. So we've already seen two examples of very naturally arising questions. How many prime numbers p are there where p minus 1 only has lots of small prime factors? How many primes p are there in the opposite case where p minus 1 divided by 2 is a prime number? These are the sorts of questions that I like to study in my day-to-day work. Unfortunately, I don't know how to answer the second question, and I can only partially answer the first question, so I still need to work harder at it. And although both of these questions came up from motivated by applications, as soon as you start getting a feel for these things, there's all these amazing different questions about prime numbers that for mathematicians who study prime numbers are just fascinating in and of themselves. So as I mentioned, there's this most important problem in mathematics, the Riemann hypothesis, which is essentially asking for good answers to how many prime numbers are there less than whatever your choice of a given number is. But here's another question, which is a particular favorite of mine. It's called the twin prime conjecture, which is asking about how close can prime numbers be together. In particular, it's asking, are there infinitely many pairs of primes which differ by exactly 2? So there's lots of prime numbers, pairs of prime numbers which differ by exactly 2, sort of 3 and 5, 5 and 7, 11 and 13. We believe there should be infinitely many of them. And in some ways, this is an even easier question than these questions. It's simpler to state, are there infinitely many primes p such that p plus 2 is also a prime number? But this question is another one of these famous 100-year-old problems that's completely unsolved. So far, hopefully I've given you a bit of a flavor, and I've maybe convinced you that prime numbers really are quite important to mathematicians, and they really do crop up in various other places. But I couldn't be too cross with you if I'd slightly given you the impression that there's all these questions about prime numbers that are maybe hundreds or even thousands of years old, and mathematicians are just completely stuck on them. And it's almost pointless to even think about these problems, because if mathematicians like Gauss weren't able to solve these problems, then what hope do modern mathematicians have of doing it? And maybe the whole of number theory and prime numbers is a bit of a dead field, that you can take a complicated question, you can turn it into some maybe slightly simpler question about prime numbers, but if you can't solve that, then the whole effort is a bit fruitless. So the key thing that I'd like to leave you with as an impression is that even though there are these famous problems that we don't know how to solve, modern mathematics is actually making lots of different progress on important questions about prime numbers, including some of these important questions. And it's a very exciting time actually in prime number theory, because we are able to say various partial results towards some of these basic questions about the distribution of primes. So, for example, here's one result that I was a part of along with my collaborators. I told you that one of my favorite problems on prime numbers is about gaps between prime numbers, and there was the twin prime conjecture, which asked, are there infinitely many pairs of primes that differ by exactly 2? We believe there should be, we don't know how to solve it. Similarly, you could ask, well, what about pairs of primes that differ by exactly 4? We believe there should be infinitely many pairs of primes that differ by 4, but we don't know how to solve it. I guess if you want infinitely many, you have to have an even number, because as we saw before with p minus 1 always being a multiple of 2, you can't have 2 prime numbers that differ by an odd amount unless one of those prime numbers is even, and there's only one even prime number, which is 2. But anyway, I can't solve p and p plus 2. I can't solve p and p plus 4. I can't solve p and p plus 6. And you can keep on asking these questions, and I can't solve p and p plus 246. But I can say that for at least one of those differences, 2, 4, 6, 8, up to 246, one of those is solvable. And so in particular, even I can show that there's infinitely many pairs of primes that differ by no more than 246. And so you could, if you have this system of, I guess, 123 different prime number equations, I know that at least one of them has the answer that we guess is true, even if I can't tell you which one. So just over 10 years ago, nothing of this was known at all. We didn't have any bound on gaps between prime numbers, even though this problem of the distribution of primes and how close prime numbers come together has been studied for over 100 years. A similar result in the same spirit, if you think that we had this question about credit card details on Amazon being secure, being a question about whether there's infinitely many primes p such that p minus 1 divided by 2 is a prime number. We can't solve that. Similarly, we found out that how often you can solve Fermat's last theorem using Sophie Germain's work also boil down to the same question. So I can't solve that question about p minus 1 divided by 2 being a prime number, but I can show you that there are some fixed numbers, I'll call them a1 and a2, such that there are infinitely many primes p, such that p minus a1 divided by a2 is a prime. So if I could do this with a1 being 1 and a2 being 2, then I would have solved the question that we were thinking about for cryptographic schemes and for Sophie Germain's approach to Fermat's last theorem. I don't know how to do this, but I am able to do some weak result in that sort of direction. And if you're someone who's worried about whether cryptographic schemes are secure or not, then maybe this gives you a little bit of reassurance that the guesses that underlie the reasons why mathematicians believe that there should be infinitely many primes where p minus 1 divided by 2 is a prime number, this is somehow very compatible with all of those thinking. And so even if we can't prove it, we're making progress towards it, and it fits in very much with everything that mathematicians expect to be true. It would be pretty bizarre if there were infinitely many solutions to this equation, but there weren't infinitely many solutions to p minus 1 divided by 2 being a prime number. And so that won't completely reassure you, but that's the best we can do at the moment for trying to reassure you if you're worried about your credit card details. So I think maybe I'll begin to wrap things up, and I'd like to just summarize the main points which I'd like you to kind of take away from today's talk. So there's lots of important questions, lots of the most famous questions in mathematics involve whole numbers. And whenever these questions to do with whole numbers, so one reason that I guess there's lots of these important questions, these questions become important because they turn out to be exceptionally difficult. That because whole numbers are somehow discrete, it turns out that these questions to do with whole numbers are notoriously difficult, and we really don't have terribly good techniques for solving them. But if these questions about whole numbers involve a certain amount of multiplication, then you might hope to break these questions down into simpler questions involving prime numbers, because we know that prime numbers are the building blocks of whole numbers. And if you understand those building blocks well enough, then you hope to understand the whole numbers. And there are various cases where this whole strategy works. And if you had good results on the distribution of prime numbers and you understood the distribution of prime numbers, you could solve this problem that you've reduced to about prime numbers, and therefore solve your original question about whole numbers. Therefore, we would like a general understanding of the possible distribution of the prime numbers, and this is something that mathematicians have studied intensively for hundreds and hundreds of years. And unfortunately, even though these are really fundamental questions about the distribution of the basic building blocks of natural numbers, lots of them remain mysterious to mathematicians. But even though they have been studied for hundreds of years, and even though they remain very, very difficult problems, we are slowly making progress, and mathematics is still an alive and vibrant subject, and it's a very exciting time to be working in prime numbers. Okay, so I think I might stop things here, and I'll pass over for questions. Thanks a lot for listening. I hope you enjoyed the talk.
Okay, thank you, James, for a fascinating lecture and for showing a subject that's really moving in front of us. There may be new results in a few years from now. Are there some questions? We will ask you to ask the questions in the microphone. There are two of them.
James, I wondered what you meant by flexible tools.
Okay, that's a good question. So if you take there's lots of different problems to do with whole numbers, and when they involve multiplication, you can break it down to a very specific problem about prime numbers sometimes. And that's a good reason to be interested in that specific problem. But lots of these specific problems about prime numbers are actually just one incarnation of an attempt at getting a general theory for prime numbers. So as I mentioned before, when we were looking at p minus 1 divided by 2 being a prime number, this was an example of one equation, and I was trying to solve that equation where all the variables were prime numbers. And my dream would be to have a very general theory which is purely about prime numbers and isn't necessarily looking towards applications, where I can have a very good understanding for a whole variety of different equations, and when you can solve them for prime numbers. And then whenever a new problem comes up involving whole numbers being multiplied together, you reduce it to some specific question about prime numbers, but you then don't need to go to some number theorist and ask them to try and solve this specific problem. You can call on this general theory. And so that's what I was hoping to get at with this idea of flexible tools, that when I think about problems to do with prime numbers, although I have some appreciation of the applications in mind, I'm really thinking about a general theory of prime numbers. And that's what I want, a general theory that can apply to whatever problem crops up. You know, in 100 years from now, there'll be different problems that people want to solve and want to understand, but I'm sure there will still be problems about whole numbers being multiplied together and therefore questions about prime numbers.
So thank you for a great talk. So why 246? Can you give some insights on the tools that led to that bound?
246 is a complete artifact of the method, that the method shows that you get some constant there, and then you have to do some slightly involved computation to work out what that constant is, and by tweaking the method you can tweak the constant. And so we try to optimize things as much as we can and to squeeze out as much of the method as we could, and it turns out that 246 is the number that comes out. But there's nothing terribly important or special about 246. There's no arithmetic significance about that at all, and probably if you worked really, really hard, then you know, you could even lower 246 a little bit. If you told me that you knew how to solve the Riemann hypothesis, if I could get 246 down to 244, I'd probably go away and I'd work really hard and I'd write a 100-page paper and we can share $1 million. So 246 is just an artifact of the method. But in terms of the techniques for that go into it, so it's a bit complicated and I can't explain all the details, but one important thing is we want a mathematical way of trying to detect prime numbers. That's always the kind of issue with prime numbers, and we know that it's exceptionally complicated to exactly detect prime numbers, and so one of the key ideas involved in this work was an approximate way to detect prime numbers. That so it was a way of, if you like, giving a score to every whole number based on how prime it was. And so this will give a high score to prime numbers and maybe a fairly high score to numbers that had lots of large prime factors and so were close to prime numbers, but a low score to numbers with lots of small prime factors. And this scoring system allowed you to approximately count prime numbers. So you're losing something because you're no longer exactly counting prime numbers, but what you're gaining is lots of technical flexibility in how you choose the scoring system and how you work with the scoring system. And so it was this way of approximately counting prime numbers that turned out to be very useful for this problem of small gaps between prime numbers.
You talked about understanding whole numbers by understanding little blocks, and I've recently discovered this notion of emergence of complex system, where the whole is more important than the sum of the little parts of it. And I was wondering if there is some notion of emergence involved here, where if you have an example of some complexity emerging from the little blocks, the simple primes.
Okay, so I think there's no sort of directly equivalent thing, but there's certainly some similar features. So yeah, where the sort of sum of the parts and understanding all the bits together is kind of an order of magnitude more difficult than any individual part. And so one common feature in these sort of approximate scoring systems, for example, is that they're very good at understanding the small prime factors of numbers, but they're very difficult at understanding the big prime factors because there are suddenly lots of constraints with these big numbers. And so I think that's not exactly the same sort of phenomenon, but maybe it sounds like there's sort of a few similar features.
Thank you very much.
Does this work?
Yep.
Yeah. So I'm guessing that numerical methods are useful for analyzing these questions, using computers for finding the prime factors of large numbers gives you some idea of theorems. And so really my question is going, are you eagerly anticipating the advent of quantum computers?
So computers sort of in some ways are exceptionally useful for these problems, and in some ways are frustratingly useless for lots of these problems. So computers are amazing for calculating lots of examples, producing a lot of data, which allows us to build up this guess in our head of how all of these complicated questions about prime numbers should work. So I mentioned, for example, that we don't know how to solve some of the questions that I mentioned today, but we're very sure of what the answer is. And when a natural question would be like, well, hang on, how sure are you when we're talking like trillions and trillions of dollars? And you better be really, really sure. And we have lots of theoretical heuristics and guesses that we can make about prime numbers, but those are just guesses. But what really makes us very confident in lots of these heuristics is that you can guess very, very specific things about the distribution of prime numbers, and then you can get a computer and you can test this. And you can see, does our guess fit with all the numerical data? And in all the cases that I've talked about so far, our guesses fit amazingly well as you could possibly hope for. And this really gives us a lot of confidence that we're on the right track theoretically. There have been cases where people have made a guess and then there's been some computations and then they've realized that maybe that guess wasn't correct. But for all the problems I mentioned here, the computations have really sort of verified what we're doing. And so computers have been very useful for building up this intuition and having lots of data that we can test our theories on. However, one very frustrating thing is that all of these theoretical questions boil down to questions about, are there infinitely many prime numbers, which is talking about prime numbers that are beyond any computational range. And there have been some famous examples in number theory where computers have led us astray, because if you compute with numbers going up to at most sort of 50 digits or so, you always see certain patterns, but we know that when you go with numbers which are much, much bigger than 50 digits, which is sort of too big for computers to calculate with, actually those patterns have to break down at some point. And so, yeah, computers are very important for guiding our intuition, but there's a very, very important major step done by trying to get a general theoretical understanding that's somewhat then independent of computation. But once you have a partial theoretical understanding, then it turns out computers are useful again to help optimize these things. So I mentioned 246 was made of optimizing the method as much as possible. So there's a general theoretical method that worked independently of any computer, and I claim no computer would have helped us solve because it was talking about infinitely many and arbitrarily large numbers. And that will give you some constant, but then to get the best possible constant, you need to go back to your computer and you need it to help. So computers are sort of a double-edged sword, that in some ways they're exceptionally useful. In other things, we really need to go to the theory, and I don't see a way around that. And so for the first side of things, one would imagine that quantum computers could help quite a bit for guiding mathematicians. For the second bit, my guess would be that quantum computers would not help at all.
Question, and then we'll have informal discussion.
Thank you. Thank you very much for the lovely talk. I'm afraid it's a brief comment, perhaps on the matter of emergence. Perhaps it's addition and multiplication, which are the simple ingredients, and primes, which are the emergent structure.
I guess there's a few different ways of understanding what emergence could mean, and that's certainly one way to think about things. I certainly think of primes as these fundamental building blocks, but I guess you could go back one step further and say that, yes, the really fundamental things are addition and multiplication, and then primes come out of multiplication very naturally. And so maybe you're on the side of Kronecker, who said that it's really just the natural numbers that are given to you by God and everything else is the work of man. And so you're saying that it's the natural numbers and addition and multiplication which are given you by God, and prime numbers are my artifact for how I think about things. I sort of feel that prime numbers are totally fundamental, but I see where you're coming from.
Alors, nous allons remercier le conférencier encore une fois. Vous êtes invité à venir prendre un verre avec nous. Alors, merci beaucoup.